Can you hear me now? Yes, thanks. Okay, Catalina, thanks a lot for the nice and it's a bit exaggerated introduction. And let me tell you just one thing. I'm not an astrophysicist, first of all, because my background is in nuclear and hadronic physics. But since almost 20 years, I have been studying also neutron stars and explosive phenomena, as gamma ray burst in particular. And I hope I will be able, essentially, to show you why somebody interested in nuclear physics and in hadronic physics is also interested in neutron stars and in explosive phenomena in astrophysics. There is this deep and old connection, and in a sense, it's something that is common also in other area. Let's say, for instance, cosmology is strictly connected with particle physics. So there is always this surprising, interesting, deep connection between the microphysics and the macrophysics on the larger scale. Okay, so first of all, since probably after everybody will fall asleep, let me tell everything in one slide so that after you can switch off. So what I'm going to speak about, essentially these neutron stars, are objects which are made, probably, but it's not even completely clear, mainly of neutrons with some fraction of protons and electrons. Let's say what is the most old and widely discussed idea about neutron stars is that they are made of those ingredients where the fraction of protons is from 5 to 10%. I will show at the end that maybe there are other ingredients, but let's start from that. And the point essentially is how they are produced, these objects. They are produced as the end point of evolution of massive progenitors. Massive progenitors means ordinary stars with large enough masses of at least about 10 solar masses, and they end their life with a big explosion, it is called supernova, and what remains is a neutron star. I will discuss all these points, but I thought that can be interesting. You know already where we are going. Which is their mass? We know, I would say, that the mass is somewhere between 1 to maybe 3 solar masses. The lowest limit is interesting, but up to a point. It's extremely interesting, the upper limit, and it changed with time. If you were asking this question, let's say some 20 years ago, a lot of people would have bet that the maximum mass was smaller, maybe 1.5 solar masses, essentially because there were no direct indications that there were really massive stars. I mean, objects with a mass larger than 1.5 solar masses. And it is really something recent, I mean, discoveries of the last few years, that neutron stars can be very massive. And this has deeper implications. But what is really surprising and characterizing neutron stars is their radius. Because you see, the sun, okay, obviously the sun has a mass of 1 solar mass, but this mass is distributed in a volume having a radius of 700,000 kilometers. And now, more or less, the same mass is concentrated in a radius of 10 kilometers. So that means essentially that this object is incredibly dense. It's by far the most dense object that we have in the universe, at least up to what we know now. And this density here means essentially a million billion times that of water. So this density is so large that neutron stars, in a sense, are almost black holes. If you shrink neutron stars just by a teeny factor, let's say a factor of 3, they are no more stable, and they collapse into a black hole. So it's really the last attempt of matter to survive before collapsing into a black hole. And this, therefore, is already something quite extreme. Another thing that is quite extreme is that they can harbor extremely strong magnetic fields. As we will see, these magnetic fields can be order of 100 billion times the magnetic field on Earth, or even larger. There are indications that objects called magnetars exist, and the magnetic field of these magnetars can be maybe 100 or 1,000 times larger than this one. And they can rotate extremely fast. So you have an object of 1 solar mass or more with a radius of 10 kilometers, and it can rotate almost 1,000 times per second. If you just compute the velocity at the equator, it is a significant fraction of the velocity of light. And there is something also a little bit technical. I was thinking if to tell about this or not. I'm not sure I have time, but maybe you heard about superconductivity. Superfluidity is something similar in a sense of superconductivity when the system is charge neutral, let's say. And inside the neutron stars, most likely there are layers which are superconducting and superfluid. And another very important point is the last one. These objects can emit a significant amount of gravitational waves. And this is something that people are desperately looking for since many years. And we have some good chance that soon, and by soon I mean in a few years, maybe 2, we will finally discover gravitational waves. So altogether, you see that these objects are superstars, are really exceptional objects having properties that cannot be found anywhere else in the universe. So this is more or less the outline of what I want to tell, and I don't know if I will be able to go through all of it. We will see. Okay? So the history itself is quite interesting, and I will certainly discuss it. And I want to tell you something about how they are produced. So they are produced in supernova explosion. I would like to show you, for instance, some video in which we have simulations of supernova explosion. And I already mentioned that they are superstars, but I want to show a little bit more detail. And, okay, how we are going to observe, they have been detected, so to say, the first time as pulsars using radio telescopes, but now we are mainly observing them with X-ray satellites. And as I was mentioning, we hope that soon, in a few years, we will be able to study them also via the detection of gravitational waves. And what can we learn from them? That will be the last point of this talk. So the history, and this is already funny because you should tell not invented, discovered, but in the case of neutron stars, they have been invented. I will tell you why. Let me put these things in a frame. The frame is what happened a little bit more than 100 years ago. It was quite a fantastic beginning of the century, because in a few years, Planck introduced the idea of quantization. Einstein produced special relativity and other things. And we started thinking about atomic nuclei, structure of the atoms, general relativity. And therefore, general relativity, is essentially a theory of gravitation. So it means essentially that we are changing, after 400 years, more or less, what Mr. Newton was telling, a new idea of how the planets are going around the sun, and so on and so forth. So you use general relativity to study, for instance, the solar system. Or you use general relativity to study the structure of a star. And as you know, there is a famous joke by himself, by Mr. Eddington, telling that only 3 people at that time could understand general relativity. One was Einstein, the second was Mr. Eddington, the third one he could not recall. So, but maybe it was true, because general relativity was something very complicated for that time, and he certainly didn't understand what he was speaking about, and apparently he organized this famous dramatic first sort of check of general relativity. It was based on observing the trajectory of light coming from far stars at the moment of some eclipse. So they sent some mission to places where the eclipse was particularly evident, and they came back and they referred what they discovered at the Royal Society, and at that moment the world was aware that general relativity was true. And okay, de Broglie means essentially again quantum mechanics, and we are going to use especially this. Probably most of the people in the audience know about these things. I mean, Pauli exclusion principle essentially tells that matter, let's call matter, electrons, protons, all these things which are fermions, cannot occupy twice the same spot, let's say. And that has a lot of consequences, because if I have a lot of matter, since I cannot put matter all in the same box, then I have to start piling matter up. And therefore, just due to Pauli exclusion principle, it means that the energy of the system, the more I put inside, the more the energy is increasing. And this already, so to say, constitutes a way of providing some stiffness to the material so that it cannot collapse. This was really some basic idea that was exploited at the very beginning to explain what neutron stars were. So, again, what people knew at that time. There was some idea about white dwarfs. I'm going to tell now what are white dwarfs. And again, Mr. Eddington was studying stellar structure, stellar evolution. So what are white dwarfs? Because white dwarfs are close relative of neutron stars. Essentially, the idea is the following. Suppose that you squeeze together material, and at a certain moment, what happens is that you are ionizing the material. That means essentially that the electrons move freely. Let's say you have a sort of gas of electrons moving freely inside a sort of lattice. Why is this interesting? Exactly for the reason that I was telling before. In the sense that Pauli exclusion principle is telling, as I said, that two electrons cannot be exactly in the same quantum state. So that means essentially that we have this electron degeneracy pressure. That means, again, that since I cannot put two electrons in the same state, when I put the second one, it is ready to go in another state with a different momentum or whatever. And so the more I put electrons inside, the more I have to raise the energy of the states that I am occupying. So that provides a sort of pressure. A pressure that is not the normal pressure. The normal pressure has to do essentially with temperature. This is a degenerate pressure, something that was unknown before quantum mechanics. And therefore, this guy, Landau, who was one of the greatest theoreticians in the years 30, 40, let's say, he already made some calculation, basic calculation. I will not have formula. Essentially, there are probably 3 formulas. And here there are already 2, so there are only 1 remaining. What was the idea? The idea was, okay, I want to try to estimate the total energy of my system, and my system is a system in which I have electrons, okay, and I have some protons. I know that I need to have essentially the same amount of protons and of electrons. Instead, it's not charge neutral, and that would provoke, so to say, a disaster, because the energy would increase very rapidly. So I have electrons and protons, fine, and I want to put together, and I want to try to estimate the energy of this system. It's quite easy to do, in the sense that the first contribution is the contribution associated with the kinetic energy, essentially, of the electron. And okay, it scales as 1 over the radius of the star. Also, the potential energy, which is due to the fact that I have the protons are interacting due to gravity. One will say, oh, but also the electrons. Yes, but the mass of the electron is much, much smaller than the mass of the protons. It's a factor 2,000 smaller the mass of the electrons respect to the mass of the protons are interacting, so it's negligible. So let us consider the protons as sources, so to say, of a potential energy associated with gravity. And this is just, essentially, the potential energy associated with gravity if I have A protons, this is the mass of a proton, and again, this object scales as 1 over r. Okay, but this is repulsive because the kinetic energy means essentially that I have all these electrons that don't like to stay too close one to the other, exactly because of the Pauli exclusion principle. And after I have this other potential that is due to gravity and is trying to squeeze the object. So who is going to win? Well, you see, this object scales as Z, the number of electrons, and this object scales as A squared, the number of protons, but squared. So that means that at a certain moment, who is going to win is the second one. So you have a maximum amount of protons because after this is going to win, and the moment in which this is going to win, the total energy is going to minus infinity. That means essentially that the system becomes unstable and it collapses. So in this very simple way, Landau could estimate the maximum mass of a white dwarfs. It was a rough estimate because it was not putting inside general relativity, etc., but just a few years later, Chandrasekhar did very right calculation, and very right calculation was only 20% smaller than the rough calculation of Landau. So you see, when somebody knows what he's doing, even if he's not doing it exact, it is good enough for many purposes. The exact number, as probably you know, is that the maximum mass of an object, a white dwarf, it is essentially an object in which you have these electrons that are supporting the star due to this degenerate pressure. The maximum mass for that object is about 1.4 solar masses, 1.4 solar masses. But what about neutron stars? That is really funny, because as I was telling, neutron stars, one could say that have not been discovered but invented by Landau. Why was that? Well, the point was that people already knew something about nuclear physics, but they did not yet know that neutrons exist. You know, neutrons are the neutral partners of the protons, okay? But they knew about protons, they knew about electrons, and Landau thought, well, what could happen if at a certain moment I squeeze so much the material so that the protons and the electrons goes very close together, and suppose that there is some neutral particle. What if? At that point, it is clear that you don't have anymore, so to say, the protons, you don't have anymore the electrons, you have this neutral particle, and this neutral particle, again, has to respect Pauli exclusion principle. So in principle, they can have an object made only of these neutral particles that does not collapse exactly because of Pauli exclusion principle. And this was done before the discovery of the neutron. The neutron was discovered in 1932, and okay, at that point, Landau published, this slide is slightly incorrect, because he had already published a very speculative paper before, but obviously he published at that point another paper slightly speculative, using the idea of the existence of the neutrons. So you see, essentially, Landau discovered, invented neutron stars before neutrons had really been found. Okay? If one reads the paper of Landau, one can be a little bit surprised, because there were a lot of naive ideas inside. But you know, he invented something out of nothing. This idea really came out of blue. So the people who really started providing some realistic idea about neutron stars were these two guys, Baade and Zwicky. And they made the fundamental point that neutron stars are supernova remnants. That was their idea. And in their paper, a lot of really realistic things were introduced. So, in a sense, they are really the people who discovered, imagined that something realistic neutron stars could exist and how it could be produced. Okay, let me already tell this point that will come again later. Compactness. So, let's go back to a naive idea, naive question mark of Landau. We have this object made mainly of neutrons, and the density of this object must be extremely large. The idea of Landau, it was already that it was a sort of giant nucleus where essentially the protons had disappeared because they had annihilated, so to say, with the electrons to produce the neutrons. So we have this object, which is big, and it has a central density of the order of the density of atomic nuclei. So at that point, it is clear that we can estimate this quantity. I don't know why this should be called probably Z, I think, but anyway. And this quantity essentially is the ratio between the mass of the object and its radius. If you do this for the Earth, you get this number. For the Sun, it's a bit larger. For white dwarfs, it's a bit larger. For neutron stars, we are approaching 1. Why this is dramatic? Because if it reaches 1, then the object collapses to a black hole. So you see, it is not 1, but it's dramatically close to 1. As I said before, these objects are so close to collapse into a black hole. And since these objects are so dramatically compact, then a classical theory would not be a good approximation. Well, very rough approximation maybe, but not a reasonably good approximation. We really need to use general relativity if we want to study neutron stars, exactly because they are so incredibly compact. Oh, these guys are famous. In particular, this guy here is very famous, Robert Oppenheimer. As you know, he was the leader of the project for the production of the first atomic bombs in Los Alamos. And they, for the first time, used general relativity to study neutron stars. They have written an equation, Tolman-Oppenheimer-Volkov equation, that is used, let's say, every day by people like me who are studying, theoretically, neutron stars. It is the equation that describes the structure of a neutron star within general relativity. Okay, what about observations? Because you see, up to now I spoke just about theory, but when it came the first evidence of the existence of these objects, and the evidence, as you will see in a moment, also is a quite interesting and surprising history. The first point that one has to make is that, okay, these objects are anyway hot. Why they are hot? They are produced at the moment of a supernova explosion. Now, if you just make some rough hypothesis of what can happen at that moment, you immediately figure out that at the moment in which the supernova explodes, you produce this object, you can measure the temperature in two ways, in degrees or in energy. And from many practical viewpoints, it makes more sense to measure the temperature as an energy. But anyway, in degrees, you can estimate that the temperature at the beginning, when you're producing your neutron star, is 10 to 11 degrees, 100 billion degrees. But you see, it doesn't tell anything. This corresponds as an energy to another unit that probably you're not so familiar with, which is the mega electron volt. But doesn't matter if you're not familiar, because I can tell you something. If you have an atomic nucleus, the typical binding energy of your neutrons and protons inside an atomic nucleus is of the order of MeV. So mega electron volt is the typical unit, the typical order of magnitude of the energy that your neutrons and protons have inside an atomic nucleus. That is the temperature that you have at the moment you have produced your neutron star at the moment of the supernova explosion. It is quite a high temperature. But very rapidly it cools down. You can try to estimate this cooling. A rough estimate is not complicated, really. And you come to the conclusion that in some 1,000 years, the temperature is down to, let's say, 10 to 6. So it was 10 to 11, and now it's 10 to 6. So it went down for 100,000, factor of 100,000, let's say. So at that point, you have your object, which is still quite hot, and you can use Stephen Boltzmann law, and you can estimate how much energy is lost because of the radiation of photons. And you get a large energy. So you say, oh, well, fantastic, I can immediately see this object. Yes, but the point is that the temperature is still large, and therefore the photons have a wavelength that is mainly of the order of 30 angstroms. And that means essentially that this is not visible light, but X-rays. That is unpleasant because from the surface of the Earth, we cannot see X-rays coming from space because they are absorbed by the atmosphere. If you look here, this is the wavelength, and this is the opacity of the atmosphere. So essentially, 100 means that everything is absorbed. We don't see anything down here on the surface of the Earth. This is visible light. Obviously, we see it. These are radio signals, and this is our X-rays. So we cannot have, let's call it a telescope working on X-rays on the surface of the Earth. Nothing comes down here. So we have to send something in the space. At the beginning, it was with balloons. Now we have X-ray satellites, okay? And it started in the 60s. So in the 60s, there was already some technology. It was already possible to put some detector for X-rays, to put on a balloon and to send outside of the atmosphere. And Riccardo Giacconi was one of the pioneers of this exploration. And what were they looking for? Well, everything, because nobody knew exactly what to expect. But in particular, they were interested in objects that could be supernova remnant. Why? For the reason that I told before. Because one could expect, well, supernova remnants, maybe there is this neutron star, or there is something that is hot, that is emitting in X-rays. And the crab was a favorite target. But what is the crab? Well, Chinese in year 1054, they registered that something happened in the sky. A new star. And this star remained visible for quite a while, and after it disappeared. Funny enough, this I really did not know. I discovered it now preparing this talk, that also in some canyon in the United States, there is some indication that maybe is connected, which also was people registered that something new was in the sky. Okay, so what was that object? Obviously, it was a supernova explosion. It was a supernova explosion in our galaxy, so it was possible to see it for a few days just by looking. Okay. So we expect that there is some remaining, these neutron stars and something else. This remained, so to say, was forgotten for a long time. But at a certain moment, they started thinking that not everything we see in the sky are stars. There is some nebula that is just something that is not a star, something that is not point-like, okay? So they discovered this crab nebula. And after it was finished in this catalog of Messier, okay? Crab nebula, this is an old, was something like that, okay? And now we see it like this. This is seen, Crab nebula, by probably the Hubble, okay? Hubble Space Telescope. And this is what remains of that explosion of year 1054. What remains visible with the eyes, okay? But what about the neutron star? So the idea was that maybe inside that nebula there was a neutron star. It was quite clear that the nebula by itself was not a neutron star, was far too big. Neutron star, as I mentioned, has a radius of the order of 10 kilometers. This object was 10 to 13 kilometers, a little bit too large to be a neutron star. But Franco Pacini had an interesting idea. He said, well, okay, it's not a neutron star, but the origin of the energy that is brightening the nebula is a central object that is still there, and is still emitting and brightening our nebula. There is something inside. Oh, funny enough, the same year, this poor guy, Joseph Shklovsky, also proposed, well, you know, there is something funny. We see some X-ray source, and maybe this X-ray source is due to the fact that there is some material from an ordinary star that is falling onto a neutron star. This, by the way, I think is more or less the figure that has been used for the poster of this, for this talk. But obviously nobody was interested in these things. So why should be this relevant or to be believed? So it was ignored, but you will see in a moment that actually is true and is quite important. So always more or less the same year, something different happened. Jocelyn Bell was a student, a PhD student, Cavendish Laboratory in Cambridge. And the idea was, okay, let's build a radio telescope. And essentially we want to explore the possibility that some signal is not really constant. There is some sort of intermediate signal. So you need to have scintillation. No? So you need to have a good time resolution, etc., etc. So they built this, they finished it, 1967 again, and they found something. Not only that there is something scintillating, but there is something pulsating, and with an incredible regular pulsation, 1.3373012. So regular. So there were only two possibilities. Or it was Catalina, who was sending the signal, but Catalina was not yet born. So that was excluded. Although they thought about that. They thought that little green men were at the origin of that emission. Therefore, what was it? And you will see in a moment. They just published it. Okay, we have this pulsating star. And this is also another, they found more or less at the same time, the year after, they found also another pulsating star inside the crab, and inside another nebula, the Vela. So at that point, it was possible to try to make some educated guess about what these pulsating stars could be. So you have something which is pulsating, a signal pulsating with a period much smaller than 1 second, which can be the source of this. It cannot be too large. Because, for instance, let's say, it's a white dwarf. White dwarfs have a radius of the order of 10,000 kilometers. Now, suppose that it is a white dwarf rotating. If you make a simple estimate, you see that at the equator, it would move so rapidly that it would lose pieces, cannot be stable. Similar for vibration, but be much smaller. So Pacini and Gold made this hypothesis. These objects are magnetized, rotating neutron stars. So that was the moment in which a theoretical idea, an invention of Mr. Landau, and after the much more refined and realistic idea of Baade and Zwicky about the fact that neutron stars could be the remnant of a supernova explosion, and even these things had been investigated theoretically, by a lot of people, but finally somebody could pin down those objects really exist, and we found those objects inside a nebula. Inside the nebula, we see a signal which is pulsating. The pulsation is so fast that cannot be a too extended object. Can be must be very compact. So it is a neutron star, a magnetized neutron star. Okay, at this point it is, oh my goodness. I think I will tell you roughly 1/3 of what I prepared, probably. Okay, after I will scroll rapidly. Let's say I finish the history, and after I scroll very rapidly, the remaining part, so that we have at least a feeling of what I prepared. Anyway, so what is the origin of these pulses? The simple idea is that you have a neutron star rotating and a magnetic field that is not exactly aligned with the rotation axis. So essentially, at that point, you have some emission of electromagnetic waves, more or less collimated along the magnetic field. But since this object is rotating, this is moving around, and at a certain moment, we are here. When the signal is pointing towards us, we see it, and after no more, yes, no, yes, no. So a pulsation is just due to the fact that this object is rotating as a lighthouse, and when the emission points in our direction, we see it, and when not. Okay, here I have more refined, I skip this because this is more refined elaboration on the same idea. Is a rotating dipolar magnetic field. Of this formula, maybe just one point. This is how this object is losing energy because it is emitting electromagnetic waves. It's losing energy, and it's quite interesting that this luminosity goes down as the period of rotation to power 4, so quite a high power. I will come back in a moment why this is relevant. Let's keep this that is technical, and I'm so late. And I was mentioning magnetic field, but which magnetic fields? How strong they must be in order to explain what we have seen. Okay, this is the distribution of this magnetic field. So here we have the logarithm, power 10, of a magnetic field of the surface. You see that typically it is 10 to 12, but even there can be something even more strong. So the normal magnetic field is 10 to 12. 10 to 12. So on the Earth, magnetic field 10 to 12 Gauss. On the Earth is less than 1, roughly 1. Weak. Magnet, strong magnet, very strong magnet is 10 to 3, 10 to 4. Sunspot 10 to 5. Strongest continuous field 10 to 5. Strongest pulsated field 10 to 7. We are still 5 orders of magnitude below 5 orders of magnitude means 100,000 below. So it's very strong. Why is it so strong? The reason is very simple. You start with some relatively weak magnetic field, but after there is a simple law that tells you that the flux of a magnetic field through a surface has to be conserved. So essentially, you start with your relatively weak magnetic field of a star before it collapses into a neutron star. And you recall, neutron stars are so small, only 10 kilometers, and they are originated with something that's much, much larger. So you scale down, so the surface shrinks, but the flux has to remain the same. So that means that since the surface is shrinked, the magnetic field has to increase, essentially as 1 over the surface. So that is how, after this is a very naive explanation, I would never tell this in a technical conference because they would kill me immediately, because they would tell me that you know very well that is not the real explanation, it's much more complicated, but the order of magnitude is correct, I would say, okay? Oh, I promised that the title was From Birth to Death, and just to be a little bit negative, let's start from death after we come back to a birth, okay? So, let's look to this nice figure. Here we have a period of rotation in seconds, and here we have the derivative of a period of rotations, p dot, dp over dt, how much the system is changing the period of rotation per unit time. Oh, it's changing because it is emitting these electromagnetic waves, at least them, and therefore is losing energy, and therefore it has to slow down. Okay? So now what happens? You see that there are a lot of objects here. These lines correspond to a given value of a magnetic field. 10 to 12 is very popular, as it was already shown before, and they roughly rotate at 1 second. These are the normal typical pulsars. Normal typical pulsars we have already seen are located here. 1 second, 10 to 12, etc. So what happens to these objects? They keep pulsating and pulsating, or better, they keep rotating and rotating and losing more and more energy. That means that the period is getting longer and longer. The frequency of rotation is getting lower and lower. So essentially, they move along this line. Let's say this guy here, slowly drift till the moment it touches this line, more or less this line. When it arrives here, this poor guy is no more able to really emit a strong enough signal that we can detect that object as a pulsar. For us, it is dead. That's the death of a pulsar. So it's very sad, but you know, there is always life after death. No? Or maybe, I don't know. You choose. So what can happen? Some of them are dead, and it's unfortunate. But the ones which are in binary systems, they can live again. Because there are these X-ray binaries. X-ray binaries are, let's say, systems which have a neutron star and a companion. The companion can be whatever, but very interesting situation, for instance, which the companion is a white dwarf, a relatively small star. Because what happens, I will show in a moment, I show already. Let's say here, for instance. This little dot here is our neutron star, okay? And this is our companion. This is very funny. You know, the neutron star is more massive, but it's 10 kilometers. The white dwarf is less massive, but it's bigger. Okay? So these objects here, they can evolve. At a certain moment, they can become larger, and there is something very funny that can happen. There is a theoretical surface called Roche lobe. What is this Roche lobe? If this object gets swollen, the moment in which it saturates this volume here, this Roche lobe, the material here cannot remain, and it has to overflow. And it overflows over this point that is called Lagrangian 1 point, and it starts rotating around the neutron star. So you have this overflow of material that has filled the Roche lobe, and it starts rotating around the neutron star. And since it is rotating, because it really overflows this Roche lobe, not only is accreting mass to the neutron star, but is also transferring angular momentum. So now we can see how it's possible to resuscitate. Because you were here, but you were lucky enough to have a twin. You were in a binary system. So what happens? That your companion is transferring mass to you, and therefore you are reaccelerating. Your period that was increasing gets shorter and shorter. And the fastest objects that we can detect, and they are really fast, the fastest object I think is roughly 700 Hertz as a frequency of rotation. They are all assumed to be recycled neutron stars, objects that have undergone this period during which they were slowing down, no more emitting, they start accreting, they are reaccelerated, and they end up with a period of rotation well below 100th of a second. These millisecond pulsars are extremely interesting because they are the fastest of the neutron stars. And in this figure, you see that there are even objects, as I already mentioned, with fantastic magnetic fields, 10 to 15. They are called magnetars, but I don't have time to go through this. This I said, okay. So this is more or less what I was saying. The rotational history of a compact star, in certain cases, is a little bit trivial, just slow down. In other cases, if it has a companion, it can reaccelerate. There is also a thermal history of a compact star. My goodness. They are hot, they cool down, but again, if they are accreting, they can heat again. So I need to tell something about how they are produced, the birth. Instead, it's too depressing. Let's go through this a little bit rapidly. So we know that the life of a star is complicated and it depends on its mass. And depending on its mass, there is a normal period of its life during which the star remains up, so to say, sustained by thermal pressure that can be normal thermal pressure of a material or also radiation pressure. Essentially, what is keeping the star up is that inside the star there are a lot of nuclear processes, like, for instance, this proton-proton chain or other more complicated chains. So this is what happens during the time in which a star has its normal life. Our sun is exactly doing this type of processes. Okay, and this is the equilibrium. Let me skip a little bit about this. So how a normal star remains up because there's an equilibrium between the gravity and this pressure. And this is a formula telling essentially what I already said, thermal pressure, radiation pressure. Oh, this you cannot read, was just to show that what happens to the star depends on its mass. So our sun should be somewhere here. I think it's probably this one. So the future of our star, of our sun, is to become a red giant and maybe at the end a white dwarf. But what if we are speaking about more massive objects? This figure here is technically but more clear, in my opinion. You see here there is the initial mass of a star. So our sun is 1, okay? But I told you that neutron stars are associated with object progenitors more massive than roughly 10 solar masses. And here it's not only just the mass. There is also another ingredient which is called metallicity. Metallicity is really something that is not so much to do with what we could imagine. It's just the the idea if there are any more the layers of hydrogen and helium, which are quite typical in the stars. So essentially an object having a very high metallicity is an object that has lost, for whatever reason, the external layers of hydrogen and helium. So essentially what's the point of this figure? That you see that there is all this area here where the star will end up by producing a neutron star. It can also happen in other cases, but if the mass is even larger, it's likely that you end up with a black hole. So how really this happens, that you produce a neutron star? You start burning inside. You started burning your hydrogen, and after you start burning other more heavy elements, you start producing more heavy elements, and you keep burning and burning up to a point in which you are producing iron. That is the problem, because the moment in which you start producing iron, the center of the star, you cannot produce other energy. You cannot generate other energy, because iron is supposed to be the most stable of all possible elements. So at that point, you have this big amount of iron at the center of the star, and you are no more able to produce energy via some nuclear reaction, but there is all the pressure of the star on top of it. Now you can say, well, but maybe it can survive. Yeah, it can survive. You see, that giant piece of iron is very similar, in a sense, to a white dwarf. But we have seen before that a white dwarf cannot exist stable if its mass is larger than 1.4 solar masses. So the moment in which that giant piece of iron reaches a mass which is more or less 1.4, maybe a little bit less, it has to collapse. And that's a moment that is anticipating the supernova explosion. Oh, this is interesting. I mean, how rapidly all these processes are proceeding. You start with a very slow burning of the hydrogen, but the last is incredibly fast. Oh. Okay, I have to decide what to tell you now, because really, I mean, I'm roughly at half of it. So let me think. I want to finish a little bit with supernova, and after I flash the other things, okay? Because supernova is quite interesting, and I have a video that I want to show you. So how a supernova explodes? So what happens, you add your progenitor, this, let's say, 10, 15, 20 solar mass object. You produce the iron. The iron core was larger, let's say, than 1 point something solar masses. At that point, the system is unstable, no way. It starts collapsing. Here, initial phase of collapse. Material goes down. It goes down, goes down, goes down till the moment in which the pressure inside becomes so large that this collapse stops. When is this moment? The moment in which, for instance, the pressure due to Pauli principle I was mentioned at the beginning starts coming into the game. Actually, strong interactions are very important, but let's keep this. So at that moment, you have reached a density which is similar to the density of an atomic nucleus. The pressure is fantastic, and the system has to bounce back. Okay, it bounced back, but after what? It stops bouncing back. So that was the original idea of supernova explosion. It was investigated for quite a while. It doesn't work, because it just bounced back, essentially. So the next sophistication was, okay, wait a moment. The system collapsed, and due to this collapse, it also became extremely hot. It is so hot that it is emitting a lot of neutrinos. Now, these neutrinos, in general, don't do anything. They just go through material without interacting, almost without interacting. The crucial adjective is almost, because there the flux of neutrinos is so extreme that it is the neutrinos who are pushing the external layers and make the supernova explode? Maybe. Maybe. So this is a more sophisticated idea about supernova explosion. That you have a collapse, you have the bounce back, is not enough, you have neutrino emitted, is it enough? No. So let me show you a state of the art of the situation. I have a video that I want to show you. There is not really there's a silly music, so I don't know if I can eliminate, but the video is nice. Please don't consider the music, it's a bit silly. Oh, it's not there, fantastic. Okay, so this video essentially is a real simulation made of what happens at the center of a collapsing star. Now, what I want to show you are very few things. You see how irregular is the center of a star. Why is so irregular? Because there are a lot of instabilities. This system, okay, it collapsed at the beginning and it collapsed in a spherical way. But after, you start with some teeny perturbation, and this teeny perturbation amplifies fantastically, and you see these objects which are completely irregular. Now, which is the last idea that people are exploring? In a moment, you probably see it. Probably if it's not already over, I think it's in the next 1 second or so. Let's see. I hope it was not already when I was looking there. Let's see. Or was already, sorry, let me show it again. Probably it was showing while I was not looking. Just a second. Yeah, okay, this tells how difficult it is, but yeah, okay, this situation here. Okay, let's go back here, let's say. You see, in particular, there is one instability. Look at this. This is a funny instability. It's the same instability that you have if you have a sink. You fill it with water, rotating. At a certain moment, this water that is falling down the sink, it starts moving this way. You can try. The water needs to rotate. It's called this accretion shock instability, SASI. Why these instabilities are important? Because every time that you are producing something which is not spherically symmetric, you are accelerating the process of expansion and you are helping the system to explode. So this is the last idea that entered the game. Was it enough to make the supernova explode in the simulation? Well, honestly speaking, no. People doing this are really trying very hard, and to my knowledge, they can obtain some very mild explosion, very mild, when the mass of a progenitor is small, but still there are very big question marks how more massive progenitors are going to explode. So this is one, you see, these people are really the big bosses in the game, Anstom-Ayanka, etc. And that means that at the moment we still do not have a clear idea of why supernova explode. Not just rough, but precise idea. We don't have. Okay. Let's keep something. Okay. This was very important to tell because we observed in 1987 a supernova exploding close to our galaxy, and we detected the neutrinos emitted, and this is fantastically interesting, but it's also very far. Let's keep a little bit. This essentially is the last point that I wanted to make, because I mentioned many times general relativity and gravitational waves. There is something that one has to know, because this is really important. As I already mentioned, there are systems which are binary systems. In particular, there is this system here made of 2 neutron stars. And why this system is so interesting? Because it was possible to measure with high precision the variation of the period of rotation of these 2 neutron stars, rotation one around the other. And this is what is shown in this figure. See where they're here. They started taking data more or less here. And this is the change of the period in time, blah, 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 blah. What is really important is that all these data points just sit exactly on top of this line, and this line is what general relativity is telling. And why the system is changing its period of rotation in that way? Because general relativity is making one, not only one, but one of many, but one very important prevision, that gravitational waves are emitted. Gravitational waves are really fantastic idea, because in general relativity, you know, mass is deforming space and time. So if mass is moving, then you form some sort of ripples in space and time, and these ripples can propagate. And this is an indirect test, not only of general relativity, but specifically of the idea that probably gravitational waves exist and are the origin of that exact prediction. We don't have time. This is one of the frontiers of research now. And these are apparata try to detect directly, not indirectly as before, direct gravitational waves. With LIGO, actually there are two of them in the United States. There is Virgo, which is relatively close by here, close to Pisa, one in Japan and one in Germany. So they are trying to detect directly, essentially in the same way we can detect electromagnetic waves, not exactly the same way, but direct way, gravitational waves. We hope in a few years to see. This is essentially, I'm really finishing, okay? I finish in 5 minutes, okay? This is the second video. And this video, in principle, also had an audio, so I don't know. I will try to see if it is not telling, I will comment. This is a video produced for the NASA by a group working in Berlin and Frankfurt. And it is about what happens when you have two neutron stars. Okay, we have already seen neutron stars rotating, it's very interesting. Yes, but now we can do something which is more. We can keep following what happens when these neutron stars are touching each other and collapsing, and they can produce a black hole. We can follow completely what happens till the very last moment. And another interesting point is that, as the video will tell, we are speculating, we are thinking that certain extremely strong bursts in gamma ray bursts, are produced at the moment in which two neutron stars are merging together to form a black hole. So let's see this video, after essentially I'm done. The video, it's here. I don't know if you can also, can you hear something? Can you? Okay.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes, Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows 2 neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
Okay, that's it. So, this is one of the things where the research is particularly active, because we have been detecting gamma-ray bursts now since quite many years. We have seen that there are at least 2 different types, the long that were mentioned at the beginning and the short ones. The origin is different. The origin of the short, most likely, is the merging of 2 neutron stars. And a lot can be learned by studying this merging. We can maybe finally detect vibrational waves. I was showing before these 2 apparata, Virgo and LIGO, and I think that next year, 2016, they will start again taking data because they went through upgrade, to say. So there is a good chance that in 2-3 years, they will finally detect vibrational waves. This was something that was imagined by Albert Einstein 100 years ago, and has never been directly found. That would be one of the greatest discoveries ever, if we find them. And we can learn a lot of things also about the structure of neutron stars. The very last slide, and after I stop, essentially is what can we learn from them. I already mentioned a few things. I mentioned vibrational waves. I have no time really to tell about this, properties of neutrinos, and this is extremely interesting, the fact that every nuclei are produced at the moment of supernova explosion, but I have no time to tell. There is one just thing, because we are in one of the big national lab of INFN. So I think that there is one point that I want to make again. There is a deep connection between microphysics and these objects. So you see, this is how can we test matter at extreme condition. Baryon chemical potential means density, essentially. Large densities, neutron stars. Large temperatures. You have probably heard that at CERN, there are experiments in which you are smashing heavy nuclei one against the other ultra-relativistically. And in that way, you are increasing fantastically the temperature of the system, but not so much the density of the system. So this is what you test in that type of experiment. Neutron stars are sitting here, is complementary. So why this is important? Because we still don't know exactly what happens to matter at that extremely, extremely high densities. And maybe we know something about the external part of a neutron star. I don't have time to go through this. After, if you are interested, I can tell you. But we know much less about the interior. We don't know what happens when the density reaches a value which is a few times the density of atomic nuclei. Other particles are most likely produced at the center of neutron star. Resonances, for instance, here, there are people studying hyperons, and hyperons are baryons, so objects similar to neutrons and protons, but containing strange quarks. it is very likely that they are produced in the center of a neutron star. But after this has a fantastic series of consequences that would be interesting to tell you also because this is what I'm working in, but I really don't have time. And even quarks can enter the game directly in the sense that when you reach this extreme densities, quark can deconfine. We even don't know if there is only one type of neutron stars, or maybe two. Let me finish with just one funny thing. Some 4 or 5 years ago, I went to a conference in Sardinia, and there was as a guest Jocelyn Bell. Jocelyn Bell, you recall, was the lady, it was a PhD student of the guy who got the Nobel Prize for discovering the pulsars, but she actually found the pulsation, but unfortunately, the Nobel Prize went to her professor, as is always the case. So she was there as a guest, and she said something that to me was really stimulating. She said, well, we still don't know if there is only one type of neutron stars. Maybe not. Maybe there are two. And this for me was a very strong, so to say, moral support, because I'm following the idea that maybe there are not only neutron stars, maybe there are neutron stars, but even more dense objects entirely made of deconfined quarks. This is really something that is speculative, but what else can we do if not to speculate? Okay, with this very confusing remark, I stop, and thanks for the attention, and thank you. Va bene.